Hello, let's have a look at the James Ruse 2022 trial question 36. This is a question written by Dr. Tammy Humphrey, who is a brilliant physics teacher. I would highly recommend that you check out some of her resources. They're very, very helpful. So you can have a read of the question. You can pause the video here. So what I wanted to go through today is I wanted to go through explaining why each section has what it has and kind of relating that to the physics, and then we can go through a little bit of extension work and think about what happens if we change like the masses. Instead of 90 grams, it might be something else. So let's get started with stage one. Let's get started with a review of the stages. So stage one is when my mass is being pulled up by the motor shaft. Okay. Stage two is when the motor's on, but the mass is no longer moving, so it's kind of just kind of stuck there, and the motor is trying to rotate but it can't. In stage three, you turn off the power source and you just let the mass fall down, and the motor spins because the mass is falling down. So now that we understand that, let's analyze stage one, stage two, and stage three. Stage one. So in stage one, we can see that the velocity of the mass carrier is positive, and that makes sense because my mass carrier is indeed going upwards because it's being dragged up by the motor shaft. We can also see here that we have, in terms of stage one, we have a bit of an interesting shape for our current. It kind of goes up and then down again. And the voltage is mostly constant. The voltage is actually really complicated. It's beyond a HSC level. I explore it in a separate video afterwards. So let's not worry too much about the voltage. It's a bit complicated. Let's have a think about what's happening here, right? So first of all, we need to have a think about back EMF. Now, if you're not confident with back EMF, I highly recommend that you check out the video that I made on back EMF. It's in the description. But we can get started with having a look at stage one. So in stage one, if you're pulling up that mass, there's going to be a bit of a problem, right? Because you can see that this mass is going to oppose the rotation of that motor. So let's have a think about the normal, what happens with a motor normally. So as a motor normally rotates, we're going to have a, because there's also, the magnetic fields here, right? You have the magnetic fields here. South. So you're going to have like the magnetic field lines here. So you're going to have a change in flux of a change in time, which is going to give you an EMF, right? So we're going to have an EMF there. And this is actually our back EMF, right? Because by Lenz's law, this EMF generated must oppose the V supply. Again, if you're not confident with back EMF, have a watch of the video beforehand. So as that motor spins, as you connect it to the power supply, it's going to spin, and that's why it's dragging up our mass. But because it's dragging up our mass, but because it's spinning, we do get that back EMF coming in. Now, if we have a look at this curve, you'll actually quickly recognize that this is a classic back EMF curve, right? So if you think about the net voltage, so we know that V net is equal to V supply minus back EMF, right? Because the back EMF will oppose the supply voltage. So we can see here that, initially the current is really high. Let's think about why that is, right? So a high current, so the current must be from the net voltage. So only a net voltage will create a current in the circuit. So if there's a high current, there must be a high net voltage. Okay, so we can see that there's a high net voltage here. And so let's have a think about this, right? If you have a big net voltage, the supply voltage is constant. The battery doesn't change its voltage, so the back EMF must be really low. And that makes sense. Initially, when we start our motor up, the back EMF is very low. Why is it very low? Well, think about this. Back EMF is from the change in flux over time. Initially, you have a lot of inertia. Nothing's moving. It's all very still, right? So you got to overcome the inertia of the coil and the inertia of the mass. So it's going to rotate very slowly. Your change in flux over time is going to be very, very small. Your back EMF is going to be very, very small. So the back EMF here is very, very small. So our V net is very, very big, which means that our net current, or like our current period, is going to be very, very big. So then why does it kind of decrease over time? Well, let's have a think about that. So our current decreases over time because as we begin to spin a little bit faster and a little bit faster, we begin to overcome that inertia, right? Well, what's going to happen is that we are going to have the change in flux over time increase, right? Because our rotation is faster, change in flux is increasing. So our back EMF is also going to be increasing. And if our back EMF increases, so if my back EMF increases, then, and V supply is again constant, you can't change the voltage of the battery, our V net must be decreasing. So if the voltage is decreasing, well then my current must, if my voltage is decreasing, then my current should also be decreasing. So that kind of explains why we have this shape here. So as it spins faster and faster, so it might decrease a little bit, and then, but there is still some current here, right? So there is still some current in the circuit. Because there is still some current in the circuit, it's a little bit tricky to write down. So because we do still have some current in the circuit, we know that torque is equal to NBIA, right? So if there's still some current, there will still be some torque. Some torque means that so torque is like rotational force. So it's going to cause your coil to spin a little bit faster, right? It's going to cause the coil to spin a little bit faster. And if you make it spin faster, again, you're going to have more back EMF, which means you decrease your net voltage, you decrease your net current, and then we're over there, and you can repeat that cycle. You're going to decrease a little bit more, decrease a little bit more, a little bit more, a little bit more, right? Cool. Let's relate that to this graph here of the velocity of my mass over time. We can see that the velocity of mass kind of plateaus, right? Let's try and explain why does that plateau. So this is the velocity, right? This is the velocity. So this is a velocity time graph. So we can see that if we take the gradient, then if we take the gradient, then what's the gradient of a velocity time curve? So we know that the gradient is nothing but the change in the y over the change in the x. In this case, the y-axis is velocity over time. Delta v over delta t is nothing but acceleration, right? So we can see that initially the acceleration is really big, and now the acceleration is almost zero. Why is that? Well, let's have a think about that, right? Let's have a think about that. We know that F is equal to ma, right? Force is equal to mass times acceleration. So if we have less acceleration, it must mean that we're having less force. Why is that? Well, let's have a think. Where did this force come from? It came from inside the motor, right? So if the force came from inside the motor, that must mean it must have came from F is equal to BIL. So the force decreased, our current was decreasing. Does that make sense? Well, yeah, we just said that, right? We can have a look at this graph here. As you have, we can see that over time, the amount of current decreases, right? And that makes sense. So if we decrease my current, if you decrease the current, then you decrease the force. And so if you decrease the force, you decrease my acceleration, right? And that's why your velocity doesn't just keep increasing at the same rate, right? The velocity will slow down. The increase in the velocity will slow down because you're having less force, because you're having less current in the circuit. Again, we're not going to explore this voltage time graph because you would expect that because you do have a back EMF, then the voltage would actually go down because of the back EMF, but it's not. It's actually going slightly upwards. And this is a pretty complicated effect. To be on the HSC, it's in a separate video. It's very optional. Let's have a look at section 2. What's going on in section 2? Well, section 2 is when you're running the motor, but it's kind of stuck, right? So imagine, you have like a drill, you're like drilling a screw into the wall, gets stuck in the wall, or gets stuck on something, and then you're like pressing the drill, but it's not going anywhere. This is what's happening, right? So like, to be very clear, it's still on. The motor in stage 2 is still on. It has not been turned off. It's still on. It's still on. So there's still electricity, there's still current flowing through the motor, right? It's still on. Because it's still on, so it's still on, and like the motor is kind of like trying to turn, but it's stuck here, so it's not turning anymore. Okay, so let's try and analyze this. So let's have a think about the vertical velocity is 0. That makes sense because it's not moving at all, so that's good. That part makes sense. Let's have a think about how we can relate that to the voltage and the current graphs. Okay, so if my motor is kind of stuck there, right, then how much change in flux of a change in time do I have? Well, 0, because it's not moving, right? If it's not, the motor is not moving, the change in flux of a change in time is 0. And so the back EMF must be 0, right? And so let's have a think about that, right? If the back EMF is 0, so if I have, you know, V net is equal to V supply minus back EMF, if my back EMF is equal to 0, well then V net equals V supply. And so we can see here that is why our voltage is constant, because I think Dr. Humphrey must have been using a 2-volt battery. So we can see that our V net is equal to our V supply. We have about 2 volts going on there. Now, we can see here again, we can see that the current increases. Well, now why is that, right? So before our V net was being suppressed from our back EMF, right? So because there was some back EMF going on, the back EMF suppresses my V net, right? Because if you have V supply minus anything, it's going to be less than V supply. So because the back EMF existed, V net is less than V supply. And so that means that we have less current than we should. Now that the back EMF is 0, V net is equal to V supply. Well, then what happens? Well, if you think about it, we have an increase in the net voltage, so we have an increase in the current, and that's why it kind of goes up there. Let's have a look at stage 3 now. So stage 3. So stage 3, we can see that the velocity is constantly downwards, is getting faster and faster downwards, and that makes sense because it is dropping. Now the key thing to realize in stage 3 is that in stage 3 our motor begins to act as a generator, right? In stage 3 our motor acts as a generator. Now first of all, what is a generator? A generator is just the opposite of a motor. So a motor acts to turn So a motor acts to turn electrical energy into kinetic energy. And similarly, we can have a generator. So a generator, something that you might use to create electricity, is turning kinetic or rotational energy into electrical energy. Yay! Now, as for the structure of a generator, the structure of a generator is identical to that of a motor. So if this was a motor, what I do is I remove the battery because again, the whole point of a generator is to create electricity for me. So I might hook up something like a resistor, or maybe like you can imagine like my phone, like because I want to charge like my iPhone, right? Right? Anything, right? And then I supply the rotational motion, right? And industrially, this might be supplied by steam that was boiled by coal, or some hydroelectric stuff, right? Or like some steam generated by like nuclear fission. So basically, it rotates here, right? And then it's going to generate some electricity. Why is it going to generate electricity? Well, because as you rotate this armature inside the coil, there's going to be that change in flux, and it generates an EMF. It's not really called back EMF in this case, it's just normal EMF. So because we have that change in flux over time, we're going to have an EMF generated, and that's going to charge my phone. Let's have a think about this one, right? So what's happening here is that as I crank my motor, we have that that EMF being generated. Now it's not being cranked by a hand, it's being cranked because like this mass is falling down, so it's spinning the armature, and we're having that change in flux over time, and we're having that EMF being generated. And you can see that here, right? You can see that here. So we can see that there is a voltage being generated, and we can see that this voltage is negative, right? It's a negative voltage. This makes sense, right? This makes sense because so when we were turning clockwise here, the back EMF says, hey, no, I don't want to be turning clockwise. I don't want to be moving at all. So you want to induce a anti-clockwise kind of motion, right? And so that was the negative voltage, right? So the back EMF was a negative voltage. So you can imagine that if we graph the back EMF would be like a negative voltage. Now we are turning anti-clockwise. So it's moving anti-clockwise here in the same direction as what the back EMF wanted us to be moving in, and so the voltage must still be negative. Okay, now let's try and explain why does the voltage get bigger and bigger. Well, that's not too hard to explain, because if we think about how we got this voltage in the first place, we got this voltage from a change in flux over time. So change in flux means that if we have rotation, right? So the faster and faster that our motor rotates, the more and more back EMF that we have. The faster and faster our generator rotates, the more change in flux that we have, the more EMF we are inducing. And that makes sense because we can see that our mass is falling, gravity is making it go faster, right? So because gravity is making it go faster, we're going to increase the rate of turning of the armature, and so we're going to see that the voltage becomes bigger and bigger because it's rotating faster and faster. The change in flux is faster, is bigger. We have more back EMF being induced. So just to recap, initially when we turn it clockwise, the back EMF says, "Hey, buddy, I want to turn anti-clockwise because it wants to oppose the motion." So we have this kind of motion, and back EMF is negative, so this must be like a negative voltage. So to turn anti-clockwise must be a negative voltage. We can see here now that we are turning anti-clockwise, we should be registering a negative voltage as well. Last question that's a little bit tricky is, why on earth is my current here positive then? If I have a negative voltage, I should have a negative current, no? Why is it positive current? This one is a little bit tricky. So positive current means that current is still turning in the direction as it used to be turning. Let's have a think about why this is. This is kind of confusing, and it's a little bit deep. Okay, so it's going to be a little bit tricky to follow along. Have you ever thought about a normal circuit? So here's a normal circuit, right? We have, this is the positive end, this is the negative end. So we're going to have current flowing from the positive terminal to the negative terminal, right? But so the current flows from the positive to the negative, right? This is what we're used to, flowing from the positive to the negative. Now, let's have a think about the current, right? So if you think about it, inside the battery, our current must be flowing from the negative terminal to the positive terminal, right? Because other like the electrons can't. Like our charges can't just like teleport. They have to flow, right? And that means that inside a battery, you actually flow from negative to positive, right? So in a battery, you flow opposite. And that's the reason here, right? So a generator is kind of like a battery, because a battery is a power source, a generator is a power source. So here we can see it's opposite, right? So the voltage is negative, but the current is still positive because it's flipped, because it's now acting as a power source. So because it's flipped, the current will still be flowing in the same direction as before. Another way to understand this is, let's have a think about this, right? That EMF, this voltage that we're generating, this is still has to obey Lenz's law. It still has to say, no, I want to oppose the motion. The motion is anti-clockwise. To oppose the motion, which direction do we go? We go clockwise, don't we? So if we go clockwise, the clockwise voltage, as before, right, was a positive current. Hence, we need a positive current here. And that is how this one works. We offer physics, chemistry, and math tutoring. For more insightful explanations like this one, head to tutorgum.com.